I'm doing the extra practice problems for you. I hope that this helps you. Okay, the first problem. A student makes silver chloride according to the following equation. The student starts with 50 grams of magnesium chloride and excess of silver nitrate. If she makes 125.1 grams of silver chloride, what is her percentage yield? Okay, we are given this information, and we are told that when she actually does the experiment, that she makes 125.1 grams of silver chloride. So to find the percent yield, remember we are going to need her actual yield divided by the theoretical yield, which is what we'll find here, times 100%, won't we? And so that's what we're going to need. So I am going to move this for right now, and let's figure out what the actual the theoretical yield is. The actual yield is what you actually make in the experiment. The theoretical yield is what we should be able to get. So we're going to start here, and we're going to go 50 grams of magnesium chloride times line, grams of magnesium chloride, moles of magnesium chloride. Okay, and every 1 mole of this, if you do the calculations, you get 95.21 grams of that. That's by multiplying 2 times the 35.45 for that, plus the magnesium, which is 24.31. And so when we do this, we have 4 significant figures here, 3 there, so our answer has to be in 3 significant figures. And so that is going to give us in 3 significant figures that moles of magnesium chloride. Okay, and so now we're going to go across the moles to get from here to here. So we have the moles of magnesium chloride, and we're going to the moles of silver chloride. There's 2 of these to every 1 of these. So that's going to give us 3 significant figures, 1.05 moles of silver chloride. So I'm going to come back over here. 1.05 moles of silver chloride times line. We're going to put the moles of silver chloride down here, the grams of silver chloride up here. When every 1 mole, you add them up, and the silver chloride we know is 35.45. Silver is 107.87, so that's going to give you a molar mass of 143.32. So we have 1.05 times 143.32 equals, in 3 significant figures, I get 100, I want to show you what I get, 150.4. But I have to have 150. This does not roll up. So I have to have 150 to 3 significant figures. So I'm going to write it like that. You could write it as 1.50 times 10 to the second, but I put my decimal place there to show that this is 3 significant figures. That is grams of silver chloride. Now we have the theoretical yield. The theoretical yield is 150 grams of that. So now we can look at her actual yield, which her actual yield was 125.1 grams. And then the theoretical yield was 150 times 100 equals, so we have 125.1 divided by 150. We have 3 significant figures, so our answer has to be in 3 significant figures. So my answer is 83.4%. So remember, to find your percent yield, you take the actual, which is what you got in the experiment, divided by the theoretical, which is what you calculate, times 100%, and then that gives you that. All right, that's our problem. We're told that we start with 125 grams of HCl. with an excess of calcium hydroxide. We got an 85.6% theoretical yield. We want to know how many grams did they actually make. Okay, so we know that, I'm going to put this down a little farther so I have room to work. 85.6 equals the actual grams that they make in the experiment, which is what we're looking for, divided by the theoretical, which we can calculate here, times 100%, right? This is the theoretical in grams. Okay, so let's find the theoretical so we can plug that in, then we'll just have one unknown and we can calculate that. And so I'm going to go 125 grams of HCl times line, grams of HCl to the moles of HCl. We know that in 1 mole there's 35.45 plus 1.01 is 36.46. Yep. Which equals, let's see, 125 divided by 36.46. 4 significant figures here, 3 here. I have to have my answer in 3 significant figures. It's 3.428. So I'm going to go 3.43 moles of HCl. All right, we're trying to go to here. That's what grams we're trying to look for. So I'm going to go like this, and I'm going to go through the mole tunnel. So we go moles of HCl to moles of calcium chloride. There's 1 mole of this to every 2 moles of this. So we're going to go 3.43 divided by 2 equals, in 3 significant figures, I get 1.715. So I'm going to go to 1.72 moles of calcium chloride. And then I can go 1.72 moles of calcium chloride times line, moles of calcium chloride to the grams of calcium chloride. 1 mole of this, we would go 35.45 times 2 plus, I'm pretty sure it's 40. Yep, 40.08. It's going to give us 110.98. There we go. And so 1.72 times 110.98 equals, I need 3 significant figures in my answer, and I come up with 190.8. So I'm going to go 191. Yep. Okay, so now I can come back over here, and I can put in my theoretical, 191 grams. Okay, so now I'm going to solve for the actual. So I'm going to take this number, 85.6, I'm going to multiply it, I'm going to divide it by 100%, and then I'm going to multiply it times 191 equals, and that gives me an actual yield of 163 grams. So her actual yield was 163 grams. I just solved for that. But first I had to solve everything to put in the theoretical, and then I was able to solve for that. Okay, the question is, which of the following are empirical formulas? Well, you can divide through by 2 on that one. So that's not. That one is an empirical formula. That's not. You can divide through by 2. This one, there's nothing you can divide through by, so this is an empirical formula. This one you can divide through by 3, so it's not an empirical formula. And then it says for the ones that are above that are not empirical, make their empirical formulas. So this one we would divide through by 2, so it would be NO2. That one's empirical. This one you could divide through by 2, so it would be C2H5. And then this one you can divide through by 3. And so those would be the empirical formulas for those particular molecular formulas that are represented there. Number 5. A compound has an empirical formula of CH2 and a molar mass of 56.12 grams. What is its molecular formula? So we have CH2 as its empirical formula, and we have that its molar mass is 56.12 grams per mole. So we will determine what the mass of the empirical formula is. It would be 12.01, which is carbon, plus 1.01 plus 1.01, which gives us 14.03. That is the mass of the empirical formula. We take the molar mass, divide it by the empirical mass, and that gives us the number that we need to multiply through by, which is 4. So we go back to this and we go C4H8, because we just multiply through by 4. And that's one of the simplest things we'll do in chemistry. Okay, number 6. A 115 gram sample of iron is burned in excess oxygen. So far we know that we have iron and we are burning it in oxygen. The result is a pure solid with a mass of, so we know that the thing that is produced has a mass of 164.5 grams. And there's just this pure solid that's formed. What is the empirical formula of the solid? So we are looking for the empirical formula of this solid. I shouldn't do this. I should go like that. Okay? And we know that that's its mass. And let's see, we started with a 115 grams of this, and this was in excess. So we can do our calculations from our limiting reactant, which is this one. Okay, so first, let's find the moles of iron, because we know this to be true from what he said. So let's find, and we don't know what the stoichiometric coefficients are here. So let's find the moles of iron, grams of iron, times line, grams of iron to the moles of iron. And so we know in every 1 mole, we look in the front, look at our chart, and it's 55.85. 5.85, there we go. So that's going to give me 115 divided by, and 4 significant figures, 2.0, and then what I have is 590. So I'm just going to go like that. Moles of iron. Now, we can figure out how much oxygen as far as mass, because we know we started with that much iron, so we got to end with that much iron. So the difference between these two numbers has to be the oxygen that was added to it. So I'm going to say 164.5 grams minus 115 grams. This is iron. This is the product, right? That's going to tell me the amount of oxygen in grams. 164.5 minus 115 equals, I get 49.5 grams of oxygen. So now I'm going to take that 49.5 grams of oxygen times line, and we got grams of oxygen down here, moles of oxygen up here, and every 1 mole there's 16.00. Because I'm not using it in its elemental form now, I'm trying to figure out what it is here. And so I've got to use this as 16, not as 32. Okay, so that's going to be 49.5 divided by 16 equals, that gives me 3.09, next digit's 3, so I'm safe, moles of oxygen. So here's my moles of the only 2 things that are in this one solid, this one, it says a pure solid, so this one solid that it has come out of this. Now, these are different numbers, so I'm going to divide them both by the smallest number, which would be this one. So I'm going to have, and I'm going to divide this by that also. I know that's going to be a 1, 3.09 divided by 2.059. This is 1.5. So what that means at this point is it's Fe1O 1.5. That's what we've come up with here. But we can't leave it like that. So I'm going to multiply through by 2. That's the easiest way to get these to whole numbers. So that would give me Fe2O3. And that would be my answer. And so you take the grams of the iron and you take it to moles, because you know, because of conservation of mass, that's how much iron there's going to be in here. We can figure out how much oxygen is in it because we've only got the 2 things, the one pure solid that's the product. So if we subtract this from this, we know how much oxygen there is, which is what we did. We figured out how many moles of oxygen that is, and then we got the ratio between them, which was this number. But we didn't want to leave this as a 1.5, so we multiplied through by 2, and that gave us this number. Okay, number 7. A gaseous hydrocarbon, and remember, he tells you right there that's something with carbon and hydrogen in it only, is burned in a combustion analysis experiment. Well, you know if it's a combustion that you're burning it in oxygen gas. So far, we have this. We know that. And it's a combustion analysis, so what else do we know? We know that we have this plus this being formed as products, don't we? And because that's all that there is, we know that this is what's formed. We don't know the stoichiometric coefficients. If 150 grams of gas produce, so we started over here with 150 grams, and it produces 412 grams of carbon dioxide, 0.6, of carbon dioxide, and 337.9 grams of water. What is the empirical formula? So we're trying to find that. So we start with 150 grams. We produce that many grams of CO2, that many grams of water. I'm just checking to make sure. Okay, so I told you in class, when we do this, we know that this represents the number of carbons that we had here. And this represents the number of hydrogens we had here. So if we can find the moles of this and this, and then we're going to multiply that by 2 because there's 2 hydrogens for every 1 mole of water. But if we can find the moles of this and this, then we can work our way back to that, can't we? So let's find the moles of this. So we have 412.6 grams of CO2 times line, grams of CO2, moles of CO2. We know that whenever in any 1 mole, we have 32 plus 12.01 equals 40. Should have that memorized by now. Okay. And so that is 412.6 divided by 1 equals 4 significant figures, 9.375 moles of CO2, which also means that in this you had 9.375 moles of carbon in this. We know that from this. Okay, so I'm going to ditch this, and now I'm going to take the 337.9 grams of water and convert that into moles of water. No, 1 mole of that is 18.02. That one I do have memorized. I should have had the other one memorized. 9 divided by 18.02 equals, and that gives me 18.4 significant figures, 75 moles of water. But remember, there's 2 hydrogens in every 1 mole of water. So in that, we're going to go times 2, and that's going to give us 37.50 moles of hydrogen. Remember, because even though there's 18.75 moles of water, you have 2 hydrogens, moles of hydrogen in every 1 mole of water. Therefore, you have to multiply it by 2. So now we have 37.50 moles of hydrogen back there. Okay, so now that we have that, we need to figure out how much, let's say how much hydrogen there is to carbon, because that's the larger number. So I'm going to say 37.50 moles of hydrogen per 9.375 moles of carbon divided by, and that gives me 4. So I know that there are 4 times more hydrogens than there are oxygens. There you go. And so the empirical formula is CH4. Now we could go back and finish this whole thing at that point, couldn't we? We could go, okay, we have a 2 here, and then we have 2. 2 is 4. It's 2. We could actually write a balanced chemical equation now that we're done with that, couldn't we? But you don't have to do that. Okay, all you had to do was get to here. And how did you do that? You took this and went to the number of moles, And so we found the number of moles of carbon that way. Then you took this and took the water to the moles, and then whatever that was, you multiplied it by 2. That was the moles of hydrogen. And then you just figured out the ratio they were between them. I would always put the larger number on top. But that told me that it was hydrogen to carbon. And so that got 4 times as much as that did. And there's our empirical formula. Number 8, a 25-gram sample of an unknown substance was burned in excess oxygen to produce 47.8 grams of carbon dioxide and 29.3 grams of water. There are no other products. What is the empirical formula of the unknown substance? Okay, so now we have an unknown that's burned in excess oxygen. So we know there's carbon in it because we are told that we make carbon dioxide and water. So we know there's carbon in it. We know there's hydrogen in it. But we don't know if there's oxygen in it. I'm going to put a Z there, but that could be a 0, couldn't it? It could not be there. We don't know. And we've got this in oxygen that's in excess. And we know we're producing CO2 plus H2O. We know that. And so from the information we're given, we have a 25.0 gram sample. So this is a 25.0 gram sample. And we produce 47.8 grams of carbon dioxide and 29.3 grams of water. No other products. So what is the empirical formula? And that's why we could have oxygen in this, but we don't know. We're going to see. We're going to figure that out. We can figure out how many carbons there are in it by this, can't we? Because the moles of carbon would be conserved. We can figure out how many moles of hydrogen are in it from this, can't we? Because they're conserved. And then we can figure out if there's oxygen in there or not. So let's do it. So we have 47.8 grams of CO2 times line, grams of CO2, moles. I'm going to put the excess up here so it's out of our way. Moles of CO2, and every 1 mole, it's 40.01 grams. I'm just going to make sure. Nope, glad I looked. It's 44.01. 44.01. So 47.8 divided by 44.01 equals 3 significant figures, 1.0, and I get 8.6, so I'm going to go to 9 moles of CO2. So that tells me I have 1.09 moles of carbon. Okay, now let's find the water. So I got 29.3 grams of water times line, grams of water down here, moles of water up here. 1 mole is 18.02. That's going to give me 29.3 divided by 18.02 equals, so that's 3 significant figures, 1.625, so I'm going to go up 6.3 moles of water. Now I'm going to take that and multiply that by 2, so that's going to give me 6.3 times 2, 3.26 moles of hydrogen, because there's 2 hydrogens to every mole of water. So I've got 3.26 moles of hydrogen that are in this. So far, so good. Now, to find out if there's oxygen in there, our mass will tell us that. And so we're going to figure out how much mass this is and how much mass that is. And then we can add them up and subtract that from over there, and that will tell us how much oxygen was in it. So we'll go, because look, this gives you the moles of carbon. So if we figure out how many grams, we'll know how many grams of carbon are in there. This will give you the moles of hydrogen, so then you can go over here and figure out how many grams of hydrogen are over there. You add those up and subtract that from 25, and you'll know how many grams of oxygen there were. So that's what we're doing. So we're going to go moles of carbon, grams of carbon. There's 12.01 for every mole. So we have 1.09 times 12.01, and that gives me 13.1 grams of carbon. Now we're going to do it with the hydrogen, moles of hydrogen, 1 mole, and we're going to do grams of hydrogen, 1.01. And remember, that is not in its elemental form, that's why it's not an H2. So 3.26 times 1.01 is 3.29 grams of hydrogen. Okay, so now we have this. Let's add these two numbers up. We have 13.1 plus 3.29 equals we're adding or subtracting. This goes to the 10th place, so our answer has to go to the 10th place. What comes out of my calculator is this, but we have to go to the 10th place, so we're going to go 16.4 grams. Okay, so now we can figure out how much oxygen. We started with 25.0 grams, and we know that 16.4 grams of that is the hydrogen and the oxygen that makes it up. So 25 minus 16.4 equals 8.6 grams of oxygen. Now that we know that, we can figure out how many moles. 8.6 grams of oxygen times line, grams of oxygen, moles of oxygen, 1 mole, 16.00 grams. And so 8.6 divided by 16 equals 0.5. I have two significant figures, so it's 0.537, so I'm going to go 0.54 moles of oxygen. Okay, so now I have moles of each of these guys. Here we go. I'm going to just try to make this a little clearer, so I'm going to write it here. And then I'm going to get rid of this part, because that we use to calculate the mass, so we can figure out how many moles of oxygen. There's our moles of carbon, hydrogen, and oxygen that are in this thing. So now we have to find the empirical formula. We divide through by whichever one is the smallest. In this case, it's 0.454. So we have 1.09 divided by 0.54, and that's going to give me, 1.09 divided by 0.54. That gives me 2 significant figures, 2.0, and that is carbon. 3.26 moles divided by 0.54 moles. I should have written the moles up here too, guys. This is moles and moles. This gives me 6.0, and this is moles of carbon, this is moles of hydrogen, and we know that that divided by itself is 1. So we know that it's carbon gets a 2, hydrogen gets a 6, and oxygen gets a 1. And how we know that is we took these moles, we divided them all by the smallest number, and that gave us 2 carbons, 6 hydrogens, and 1 oxygen. So that's how you would do that one. Number 9. What is the percent composition for each element in KClO3? Okay, to find the percent composition, first we want to know what the whole thing, the mass of the whole thing is. So we would say 3 times 16, which is 48, plus 35.45, which is the chlorine, and the potassium is 39.10, plus 39.10. And so the molar mass of this is 122.55. And yes, we do go to that significant figure because we added up and they all went to the 100th place. So that is the molar mass of that. Now we would take each one and figure out what percentage it is. So the potassium was 39.10 grams for potassium out of this whole thing. And then we would go times 100%. And so that would be 39.1 times 100 is 31.92%. Then you do the next one. Chlorine is 35.45 grams per the whole thing. Which is, oh, shame on me, times 100%, which is 28.93%. That's chlorine. This is potassium. And then the last one is oxygen. There's 3 oxygens, so we're going to have to do 3 times 16, so it's 48.00 divided by 122.55 times 100%, and this is for oxygen. And so we get 48 divided by 122.55 equals, and that gives us 39.17%. Now I did all those significant figures. I looked to one past them in each case and either rolled up or down as I was supposed to. Yeah, that's supposed to be a 2. Okay, because the digit after it's a 5, so it rolled up. Okay, so that's how you do that. You just add up the entire molar mass, and then you take each element, how much mass that is of each element, and divide it by the total, and then multiply it by 100, and that gives you the percentage that's in there. Number 10, a sample of an unknown substance is decomposed and found to be, so we have 59% strontium, 8.0% carbon, and 33% oxygen. What is the empirical formula? Okay, so if we were just to make each of those grams, and that's what we're going to do, we're going to go 59 grams of strontium, and we'll figure out how many moles that is. Times line, grams of strontium, moles of strontium. I think I've told you in class, if all else fails, go to the moles. Strontium weighs, its mass is 87.62. So when you do this, you end up getting 0.67 moles of strontium, 2 significant figures. Then we do carbon, 8.0 grams of carbon times line, 1 mole of carbon, 12.01 grams of carbon equals, and that also gives us 0.67 moles, but this time it's carbon. And then the oxygen, 33 grams of oxygen times line, grams of oxygen, moles of oxygen, 1 mole, 16.00 grams of oxygen. That gives us 2.1 moles of oxygen. Okay, now we have to divide through by the smallest number. And it gives me 1 strontium, 1 carbon, and 3.1 oxygens, which is close to a whole number. So we would go back and go 1 strontium, 1 carbon, and 3 oxygens. And that would be our empirical formula for that problem, which is actually strontium carbonate, isn't it? Because you've learned your polyatomic ions, so that's strontium carbonate. Okay, and then number 11, give the chemical formulas for the following substances. Ammonium oxide. Well, you have ammonium memorized is NH4 plus 1, and oxide is -2, so we're going to flip-flop the charges. So to do that, you're going to put parentheses around this. This gets the 2, and that gets the 1, so that's ammonium oxide. The next one is sodium sulfate. Sodium, you know, is a +1. It's in group 1. Sulfate is a -2. So this one gets the 2, this one gets the 1, and that would be sodium sulfate. Next one is magnesium phosphate. Magnesium is in group 2, so it's a +2. Phosphate is PO4 -3. You have that memorized. So the 3 goes down here. The 2 comes over here. So I'm going to put parentheses around it and put the 2 there. And that's magnesium phosphate. And then cobalt-2 carbonate. Cobalt-2, so you're told the charge. Carbonate is CO3 -2, and therefore this is a 1-to-1 relationship, so that would be cobalt carbonate. You might want to write them a little closer together, but that would be cobalt carbonate. Okay, those are the extra practice problems. I hope this helps you. Keep working the problems and try to see what's going on. You're usually going to go to the moles on most things, and if you need more help, let me know, please. God bless you. Have a Jesus-filled week.